Hello everyone, welcome to Lattice Semiconductor Developers Conference 2024. In these breakout sessions, I'm going to cover the topic of embedded software development using Lattice Golden System Reference Design. My name is Yao Wai. I work as an applications engineer at Lattice Semiconductor, specializing in embedded system applications. I'm responsible to enable customer and providing support for our RISC-V processors, software drivers, and applications. With over 17 years of experience, I work in Intel Programmable Solution Group in FPGA soft-core processor and SoC products. I hold a bachelor degree in mechatronics engineering from University Science Malaysia. Here's the agenda for today's presentation. First, I will talk about the TCP/IP protocol overview. Next, we will look at the Golden System Reference Design hardware architecture. Right after that, we will look at the FreeRTOS TCP/IP software, and this covers the introduction, the software architecture, as well as the operation. And then we shall look at the design demonstrations and some of the results that this design demonstrate. I will also provide a few summary on the key takeaways from this presentation, and finally address some of the frequently asked questions that we often receive. Before we start to talk about the TCP/IP software example in this design, let's quickly go through the protocol overview. Here is the overview for TCP/IP. On the left, it shows the TCP also stands for the Transmission Control Protocol. It is the communication standard that enables application program and computing devices to exchange messages over a network. It is designed to send packets across the internet, and TCP ensures the successful delivery of data and messages over the network. And at the middle is the Internet Protocol, or IP. So this is the method for sending data from one device to another across the internet. So in the IP case, every device will be assigned a unique address that is used to identify the device and solely for communication purpose with other devices. And both the TCP and IP forms the foundational protocol suite for the internet, which enable higher level protocols such as peer-to-peer sharing, including the File Transfer Protocol FTP, Secure Shell SSH, and Telnet. Also, it enables emails exchange, including Internet Message Across Protocol IMAP, Post Office Protocol POP, and Simple Mail Transfer Protocol SMTP. And also that enable the web browsing such as Hypertext Transfer Protocol HTTP. Now let us look at the hardware architecture of Lattice Golden System Reference Design. This is the block diagram for Lattice GSRD on the Certus Pro NX FPGA. On the center of the block diagram is the RISC-V RX processor, and for the memory system available in the GSRD, it offers the system memory, which uses the FPGA on-chip resources. This is a small memory and primarily used to hold the bootloader program. For larger applications that require more memory spaces, the GSRD offers the external LPDDR4 memory control via the memory control block as shown here. And for non-volatile memory, the GSRD also offers the quad SPI flash-based controller that can communicate with the external flash device. And for the Ethernet communications, there is the TSE or Triple Speed Ethernet MAC and the SGMI 5 for Ethernet. And the scatter-gather DMA is used to transfer data between Ethernet and the memory. Finally, the GSRD also offers several peripherals including GPIO, UART, configuration block for the SFP module, and also configuration block for controlling the FPGA program and configuration. All these IPs are connected via the AXI4 interconnect as well as the APB interconnect. Now let's look at the hardware operations for the GSRD. The RISC-V processor runs the FreeRTOS kernel and the TCP/IP software stack that is being stored in the external LPDDR4 memory. For sending Ethernet packets, the data is transferred from the external LPDDR4 memory to the TSE MAC via the SGDMA. And for receiving Ethernet packets, the DMA transfer data received on the MAC to the LPDDR4 memory. For connecting to the Ethernet cable, the Lattice Certus Pro Versa board offers the SFP connectivity. An SFP module with the external 5 and RJ45 connector is required. In this section, we will look at the FreeRTOS TCP/IP software that is demonstrated on the Lattice GSRD. This is the introduction to FreeRTOS plus TCP network stack. FreeRTOS is an open source real-time operating system or RTOS that is widely used in the embedded system. Lattice Propel 2 provides FreeRTOS kernel that can be used on the RISC-V RX processor. The FreeRTOS plus TCP is a scalable, open source, and thread-safe TCP stack that is used for the FreeRTOS kernel. The stack provides a familiar and standards based on Berkeley's socket interface. The list of API is as shown in the screenshot here. The FreeRTOS plus TCP feature and also the RAM footprint are fully scalable. It can be applied to a smaller low-throughput microcontrollers as well as scale up to the larger, higher throughput microprocessors. Now let us look at the features of the FreeRTOS plus TCP network stack. It supports IPv4, IPv6, and multiple network interfaces as well as network endpoints. It is fully reentrant and thread-safe API. It includes support for ARP, DHCP, and other protocols as listed. For address assignment, it supports both static and dynamic address assignment. The network stack has close integration with the FreeRTOS kernel, where it can be seamlessly integrated with the FreeRTOS task management for multitasking capabilities. It provides two types of buffer allocation that match for different embedded applications. The first scheme one is whereby the Ethernet buffers are statically allocated at compile time. This is for better runtime performance. For scheme 2, the buffers of the exactly required size are dynamically allocated and free as required during the runtime. This has slower performance compared to scheme 1, but it has efficient memory usage were typically ideal for small embedded systems. This diagram shows the software architecture for the FreeRTOS software stack. Let's begin from the bottom layer. The hardware layer represents the Golden System Reference Design or GSRD. Next is the device driver layer. This layer provides the software drivers for all the IPs used in the GSRD. For example, the Triple Speed Ethernet, SGDMA, and others. Next is the network interface layer. This is a software layer that responsible for the communication between the upper FreeRTOS TCP stack and the vendor-specific drivers at the bottom. Now, next, this is the FreeRTOS TCP stack. This is the network stack code that is coming from the FreeRTOS open source project. And finally is the application layer. In this example, we are using the TCP Echo client application where it sends messages to the host via TCP protocol, and then it receives echo messages from the host. All these software layers interact with the FreeRTOS kernel that provides the task scheduling as well as the system management. Now, let us look at more details on each of the software layers that described previously. First, let's start with the device drivers. The main drivers that used in this software example are the Ethernet driver and the SGDMA driver. For Ethernet driver, it is primarily used to set up the IP registers and also the MAC address in the controller itself. For SGDMA driver, it requires more integration with the FreeRTOS stack because it needs to allocate the network buffers where the structures are defined by the FreeRTOS stack for the SGDMA to perform data transfer. And the SGDMA interrupts in the case of transmit and receive are enabled. This is to avoid polling. Interrupt handlers are required to handle the Ethernet packets that being received and then as well as to release the network buffers. Next, let us look at the network interface layer. As shown in the diagram at the right, the network interface layer resides between the FreeRTOS TCP software stack and the driver at the bottom. It has a list of APIs or application programming interfaces that requires every vendor to implement for their platform. The list of APIs that has been created for Lattice platform are shown in the table here. We shall look at each of these in later slides. At the top of the FreeRTOS software architecture is the application layer. The TCP Echo application is used in the demonstration here. It demonstrates the communication between the client or the Lattice development board and the server. The code is used from FreeRTOS upstream, and it is implemented as a FreeRTOS task, namely Echo client task. By referring to the diagram here, the task starts by creating a FreeRTOS socket using the API provided by the network stack, and then it starts to establish a TCP connection to the server by performing a three-way handshake. If the connection is successful, the task will create a random string of data and then send the data over TCP to the server. Next, the server, upon receiving the data from the client, it shall echo back the data back to the client, and the client is designed to pending to receive the data. Now, upon receiving the data, the task will compare the data with the one that has been sent previously, and if any mismatch or error is encountered, it shall report that. Otherwise, the task will proceed to close the network socket upon all the operations has been completed. And then the task will repeat the process again by starting over to create a new network socket and continue the process again in loops manner. This diagram shows all the tasks that have been created in this demonstration as well as their relationship. On the left is the echo client task, which has been discussed in the previous slide. To quickly recap, this task creates sockets, connection to the server, and then send and receive data, and finally close the connection. On the right is the Emac handler task. So this task handles the events when the DMA and Ethernet interrupt are triggered. The handler shall release the network buffers upon a transmit completion, and for receiving packets, the handler will process it and then send the packets to the IP task. And at the bottom is the IP task created by the FreeRTOS plus TCP stack. This is the task that is responsible for all the sockets processing, handling the protocol needs such as ARP, DHCP, and all other stuff, as well as the TCP transmission and receiving. The network buffers are required by the FreeRTOS plus TCP network stack. All the Ethernet frames for sending and as well as receiving are stored in the network buffers. The network buffer descriptor is used to describe a network buffer. In a simplified form, the network buffer descriptor is shown in this diagram here, where it has a field to describe the data length of the Ethernet frames or packet, as well as a pointer to where the network data is being stored in the memory. The number of network buffers can be configured in the FreeRTOS ipconfig.h header file by using this C macro ipconfig num network buffer descriptors. A total of 48 network buffers are used in this demonstration. As described in the introduction slide, the FreeRTOS plus TCP provides two types of schemes to allocate the network buffers. Scheme 1 is used in this demonstration, where it statically allocates the network buffers. The code is implemented in the network interface layer. It starts by declaring a static array of total network buffers in the RAM. Next, for each of the network buffer descriptor, it is initialized by assigning the Ethernet buffer in the RAM to the network buffer descriptor. Then it increments the pointer to the next descriptor and complete the assignment for all the 48 network buffers. The network interface initialize is another API implemented in the network interface layer. It is responsible to initialize the hardware in the GSRD. This includes the SUDMA and register the DMA interrupts callback for both the transmit and receive case. Also initializing the TSC MAC and setting the MAC address. This API also creates the Ethernet MAC handler task that described previously, and also the counting semaphore, which is used to keep track the SCDMA descriptor usage so that the descriptor overrun would not happen. The network interface output API in the network interface layer is responsible for sending the Ethernet data. Ethernet data to be sent is passed from the IP task, where it is encapsulated in the network buffer descriptor. The data size is decoded from the descriptor, and the API will check if there is SGDMA descriptor available for transfer. If that is successful, the API will construct the DMA descriptor per the information being passed, and then trigger the DMA transfer to start the Ethernet transmission. For receiving Ethernet data, the SGDMA RX descriptor needs to be set up during the initialization. The DMA destination is set to the network buffers that has been allocated, so that the DMA is ready whenever any Ethernet data comes in. Then the DMA will automatically transfer the data to the appointed network buffers. Upon the transfer complete, the DMA will generate interrupts. In the DMA RX interrupt handler, the handler will retrieve the Ethernet frame that being received and send it to the IP task for further processing. We shall look at more details in the upcoming slides. Now, let's discuss more on the SGDMA interrupt operations. Both the SGDMA transmit and receive interrupts are enabled and registered to their associated callbacks, as shown in the diagram here. In the callback, a delegated or delayed interrupt processing method is used. The actual processing of the interrupt shall be handled by the Emac handler task that created in the FreeRTOS kernel. The interrupt callbacks in this case shall only set the corresponding TX or RX flag to notify the handler task in later stage. Once that is done, the callback will yield to the handler task from the interrupt service routine. As mentioned in the previous slide, the SCDMA interrupt operation is delegated in the Emac handler task. Now let's look at the Emac handler task in more detail. So this is triggered after the SCDMA callback to notify to this task that with a flag that some event had happened. Based on the flag set, the Emac handler task shall process the corresponding events accordingly by calling the subsequent API to process whether it's for the RX case or the TX case. We will look at each of them in the coming slides. This slide describes the process RX API that is responsible to handle the Ethernet receiving frame interrupts. So it will read the received SCDMA descriptor to understand where the Ethernet frames has been stored by the DMA. After that, it shall send the received Ethernet frame to the IP task for further processing by calling the FreeRTOS API as shown here. Next, this API also set up a new network buffer descriptor so that it can point this new network buffer to the SCDMA RX for the next operation. This means that the next incoming Ethernet frames will be stored in the buffer described by this buffer descriptor. Next, this API also releases the current network buffer descriptor in the case where the received Ethernet frames has error in it, or there has been a failure happen when passing the Ethernet frame to the IP task. In both cases, the current network buffer descriptor no longer in use and shall be released immediately. Otherwise, if the received Ethernet frames is either valid or the passing to the IP task has been successful, then the associated network buffer descriptor shall only be released by the IP task after it has completed the processing of that frame. For processing the SGDMA TX interrupt, the API first will get the current completed SGDMA TX descriptor. So this means that the Ethernet frames has been successfully sent through the Ethernet interface, and the SGDMA TX descriptor no longer needs to be used. So by referring to the TX descriptor, the API will map the descriptor to the corresponding network buffer and release the network buffer accordingly since the data has been transmitted. And finally, the API will also release the SGDMA semaphore so that to indicate that in the next processing, there is available DMA descriptor for use. We have discussed the GSRD and the software architecture for the FreeRTOS TCP+. Now, let's look at how all these are put together in the design demonstration. In this demonstration, we are using the Lattice Certus Pro NX Versa board as shown in the diagram here. For connecting to the Ethernet via the RJ45 connector, an SFP 1000 base T RJ45 module is used as shown here, and this is connecting to the SFP cage on the board. Ethernet and USB cables are used both for the Ethernet data transfer as well as programming the FPGA via the USB cable. For the software used in this demonstration, it includes Wireshark for packet analysis, Hercules for TCP echo server, as well as serial terminal software program. The upcoming slides show the steps to run the demonstration. It starts by programming the GSRD bitstream to the Certus Pro FPGA by using the Lattice Radiant programming tool. In the second step, we set up the serial terminal. Since the RISC-V RX processor in the GSRD prints messages via the serial port, the terminal enables us to see the messages being printed out. In this demonstration, Teraterm serial terminal is used, but any other terminal also can be used. The setting for the serial terminal is as follows. Using 115200 as a baud rate, 8-bit data, no parity, and no flow control. As discussed previously, the application run in this demo is the TCP Echo client application. Hence, on the server or the PC, we need to launch the TCP server. Example software used here is the Hercules software. So on the TCP server tab, we set it to listen to port number 7. This will be the primary port used for the communication between the client and server. And we also want to check the server echo option at the bottom so that the Hercules software shall echo back whatever data being received from the client. In this step, we will launch the Wireshark software to capture the packets on the Ethernet interface. This is used to analyze the Ethernet packets in the results section later. The final step is to run the TCP/IP software on the RISC-V RX processor. This is done by using the Propel SDK tool, particularly the OpenOCD debugger, to download the software to the RISC-V memory. In the screenshot here, it shows the debug configurations in the Propel SDK tool. The RISC-V FreeRTOS TCP software executable or the EOF file will be downloaded to the external memory in the GSRD, and processor shall run it upon starting the debug. After the TCP/IP software starts execute by the RISC-V processor, here are the print messages displayed on the serial terminal. First, on the first stage here, it shows the hardware initialization process, where the Ethernet 5 has been initialized to configure the SFP module via the I2C operations. When the 5 initializations has been completed, the TCP stack software will start the connection to the server by establishing the three-way handshake. Upon a few attempts, the connection to the server is successful. Once the connection has been established, on point number 3 here, the software will start send data to the server and receiving it back via the echo. So example, on the first attempt, it sends 136 bytes of data to the server, and upon receiving the same echo data back, it checks for if there is any data mismatch. If not, then it shall proceed by reporting the status. In this case, receipt is okay, and then it closes the connection, the current connection, and the process repeats again. As you will see in all these subsequent printout here, different sizes of the Ethernet packets has been constructed and sent, received via the Ethernet interface. We can also observe the same results in the Hercules software. When the Hercules software received data sent by the client, it will display in its own Receive Data tab, as shown in the screenshot here. This further aligns with the result we have discussed in the previous slide. Next, we will be focusing on the Wireshark analysis. Before we start analyzing the packets captured in Wireshark, we shall first look at the IP addresses used in this demonstration. The server IP address is shown here as 169.254.221 and 244. And the client IP address, which represents the Lattice development board, is at 169.254.221 and 245. The client MAC address is set at this value as shown here. Based on the screenshot in this diagram, we first look at frame number 8. This is where the client starts sending the Address Resolution Protocol or ARP broadcast request. This is requesting for the server that it's trying to connect to. Particularly, it wants to know what is the server MAC address. On frame number 9, the server received that broadcast request previously from the client and the server now reply its own MAC address back to the client. As discussed previously, the FreeRTOS task will start by establishing a connection to the server, and this is achieved by doing the TCP three-way handshake. So continuing the Wireshark analysis, on frame 12, we actually see the client sending a sync to the server. This is the start of the three-way handshake. On the next frame, number 13, the server responds with a sync ACK, and finally on frame 14, client end it with an acknowledgement, and this complete the three-way handshake, and a TCP connection between client and the server has been successfully established at this point. Now, after the TCP connections has been successfully established, the client will start sending data to the server. This is shown in frame number 15 here, where an echo request has been sent. And next, frame 16 is where the server echo or respond back the same data. This is because the Hercules TCP server has been set up in the PC or server, so it is able to respond back. And this is captured in Wireshark accordingly. And finally, in frame 17, the client responds back with acknowledgement after receiving the echo data from server. On the final stage, where the TCP echo send and receive has been done, now the client starts by doing the connection closing. It starts by sending the fin command to the server for closing the current connection. On frame 19, the server responds with an acknowledgement for the request. And frame 20, the server sends its own fin command back to the client. And finally, client acknowledges to the previous fin command, and the TCP connection is now successfully being closed. This is to conclude the sharing today on the FreeRTOS TCP software stack for Lattice Golden System Reference Design. The key takeaways here is, first, the Lattice GSRD provides the Ethernet capabilities that enable more complex applications such as FreeRTOS TCP IP. Next, the FreeRTOS TCP IP network stack, it requires the vendor-specific device driver as well as the network interface layer. This has been enabled by Lattice in the demonstration that shipped. And finally, the networking applications can be developed on top of the FreeRTOS TCP network stack. This enables customers to develop their own application using the open source and industrial standard network stack such as the FreeRTOS one, and they can quickly create their own application. Thank you for your time for attending this breakout session, and we truly appreciate your feedback to help us improve better. Before we end today's breakout session, I will address some of the frequently asked questions. Now, the first question: what is the clock frequency for the Ethernet path in the Golden System Reference Design? So the clock frequency is set to 125 MHz for the Ethernet, TSC MAC, SUMII, and the SGDMA. Question number 2. Why is the memory allocation scheme 1 in FreeRTOS TCP Plus is chosen for this reference design? So we chose scheme 1. Again, that is the statically assigned memory allocation. Is mainly for the runtime performance. So since the network buffers are allocated during build time, so the runtime performance is better in this case. And also since we are using the external memory, the LPDDR4 memory, so we are not constrained by memory spaces. Question number 3. How do I change the network buffers configuration? So the FreeRTOS TCP plus software stack actually provides several configurations that user can make on the network buffers. And this is done by changing the C macro in the FreeRTOS IP config header file. Question number 4. What is the code footprint for this reference design? So including the FreeRTOS kernel, the network stack, and also network buffers, the code is now compiled at close to 400 kilobytes. And final question, what is not supported in the current reference design? So in this iteration of the reference design, the IP address is now being statically assigned to the client or the device itself. So IP address assignment via DHCP is currently not supported. Thank you for listening and have a great time in Lattice Developer Conference 2024.